Hello, chemistry enthusiasts. I will be performing several demonstrations in this video. This video accompanies the types of reactions lab that we will be doing, or more to the point, will also be demonstrated as part of the types of reaction laboratory experiment. And so let me jump right into things. As I said, we're going to be talking about the conductivity of ionic compounds, of ionic solutions, and of reactions. But the first thing I want to do is discuss this apparatus that you see here. This is commonly referred to simply as a conductivity apparatus. You can see there are a couple of wires here. It's plugged into a standard outlet. And you can also see the two electrodes hanging down there. Clearly the light bulb is not on, and that is because the circuit is open. So I've got a pair of scissors here, which is really just a source of metal. And we know that the metal conducts electricity. So if I put that on both of those, there we go, the light bulb comes on. And that's because the scissors allow electrons to flow from one electrode to the other. The message here is that anything that I do that allows electrons to flow or charges to flow suggests that there are ions existing in whatever it is that I'm testing. Okay, so the first thing I want to test is the conductivity of water. Now, if we were in class, I'd literally ask you, but right now all I can do is figuratively ask you if water conducts electricity. And I am sure, because I have asked this question before in many class, that many of you are already thinking and perhaps have already said that yes, indeed, water conducts electricity. So what you just saw me pour out was some water. Pardon me, I just realized I got the wrong one. It does help if you have the right materials. So I'm getting some water. And as I've said before, these bottles of water that you can get from the store, while they are not strictly speaking distilled or deionized water, they are pretty close. So there it is. The water is in there. Now, you know, the light bulb is not on, not in the least measurable or observable extent. So our conclusion must simply be that the water does not conduct electricity. Now, if you were inclined to say that water does conduct electricity, I suspect that is because you have seen some movie or heard of something about people perhaps being shocked or electrocuted while they were in contact with water and an electric source. Well, that one is a little bit of Hollywood in action there. And while it is the fact that water does not conduct electricity, it is also the fact that there still is a hazard if there is water. Now this time you can see I've got this one labeled tap water because I filled this before I started this, and this is the one I want to do now. So I pour the tap water in there, and okay, it's not nearly as bright as when I started, right? That was an enormously bright light, but you can see the filament is glowing. So there is some flow of current through the water. So we say that this is somewhat qualitative, right? I'm not putting a number on it, but you know, if I use the words low conductivity, I think you'll understand. So what is it about the tap water that conducts electricity, whereas the deionized water, or I should just call it water, does not? So I am going to share screens now. There we go. And what I want to provide is for tap water, excuse me. There we go. For tap water, there are many materials we typically just refer to generically as minerals in the tap water. Now, this does not mean that the tap water is unsafe in any way, shape, or form. It just means that these ions exist. And so these are typical cations that exist in much of tap water. There's usually some chloride, perhaps some bicarbonate or hydrogen carbonate anions, and certainly some other ones to lesser extent. The presence of these ions, even in low amounts, does give rise to some conductivity. So those are the things that make the tap water conduct electricity. Okay, well now, there I am back live. I want to provide or look at a few other ones. And this time, I should, there they are, make certain I have my safety glasses on. You can see that this material is barium chloride. And I'm going to dump some of the barium chloride into the container. So you can see I've got barium chloride sitting there in the bottom. Now, that doesn't work all that well. Let me pause this video and I'll be right back with you. Okay, so I'm back with you, and what I've done is I've just transferred that barium chloride to a smaller container, and I put the electrodes in there. I'll get it in just a moment. Let me try it this way. There we go. I put those electrodes into the solid barium chloride, and the light bulb is not on. Now, at this point, of course, you should know that barium is a metal. You'll find it on the far left-hand side near the bottom of the periodic chart. And chloride or chlorine is a non-metal, so that barium chloride creates an ionic compound. So if this is an ionic compound, and we know that the presence of ions allows current to flow, why doesn't the bulb come on? And that is, of course, because the ions are locked into the crystal structure. They're not free to move. Okay, well, if I continue with this, now let me put a little bit of the barium chloride back in my container. Let me use just a tiny bit more, just for good measure. Okay, now I'm going to use the bottle of water that is the purified water. That is to say, I have not grabbed the deionized water. And, you know, I pour the water in there. And of course, it gets cloudy for a moment. That's simply because the material has just been suspended a little bit. So let me get something to stir this with. So I'll stir that up. And as I'm stirring this, of course, well, I say of course, I happen to know it, it will dissolve. Now, please note that not all ionic compounds dissolve. Some of them are simply insoluble. So while I'm stirring this, and set that aside. So I now have a solution. It's still a little bit cloudy, and again, that's just because it has not fully dissolved, but I don't need it to, because now the light is on, clearly very, very bright. The barium chloride has dissolved, and we say it has dissociated, right? It was associated as a molecule or as a formula, and it has disassociated so that it is individual ions. So I'm going to label this one barium chloride and set it aside for a moment. So again, setting that one aside and grabbing another container. Pardon me. What I'm getting now is a solution of sodium sulfate. So, right. So here's my solution of sodium sulfate. Sorry, I didn't have the solid available. All I had was a solution of sodium sulfate. But, whew, yep, clearly very bright lit bulb, no question about that. So the sodium sulfate is ionic, and it does dissociate. Now, I need to transfer a little bit of this. So I'm going to transfer some of that over into another container. And when I'm done with this demonstration, I'll write out what these reactions are. So here's my container of sodium sulfate. I'm going to add a little bit more water to that. A little bit more water. Now, what I want you to watch, and of course you can just back up the video if you don't quite catch it, is I'm adding the barium chloride in my right hand into the sodium sulfate in my left hand on 3, 1, 2, 3. And you see the immediate formation of a precipitate. We call it a precipitate for the same reason that when rain falls out of the sky, it's called precipitation. It is the formation of something that falls out of solution. Now I'm going to set this aside so that I can walk through what that reaction was. So pardon me while again I pause video for a moment. Okay, here we are again. So you just saw the reaction. Now let me walk through what that reaction looks like in terms of writing the chemical reaction. So the first thing we saw was barium chloride. It dissociated to give a barium ion and 2 chloride ions. When you write these reactions, please do not write something like that, the dichloride, dianion or something. If you write this, frankly, what it tells me is that you have virtually no clues to what's going on with regard to writing chemical reactions. I don't say that in a mean way. I'm just saying that, you know, if you're writing something like this, then you're demonstrating to me that you simply don't understand what these chemical reactions mean. I'm going to cross that out. The second one that I showed you was a solution of sodium sulfate. Now, if I had the solid material, it would have also been a white solid. And white solids typically provide solutions that are clear and colorless. So those are the two compounds that we used. Now, in terms of a chemical reaction, it looked a little bit like this. The barium chloride reacts with sodium sulfate to give barium sulfate plus sodium chloride. We call this a double displacement reaction. The sulfate's going over here, the chloride's coming over there. So these are the products of that reaction. Now I happen to know that barium sulfate was the solid. In this case, it's obvious that it's not the sodium chloride because we know sodium chloride to be soluble. So in this case, it's pretty obvious that it was the barium sulfate that was insoluble. These are the products of the reaction. You cannot balance a chemical reaction until you have the proper products, but this equation as written is not balanced. This one is pretty trivial to balance. I see I have 2 sodiums here, 2 chlorides there. I put a 2 right there, and that is balanced. We call this a molecular equation. I want you to keep that in mind because later on in a subsequent video, I am going to tell you that you need to write the molecular equation, total ionic equation, and net ionic equation for the reactions that you're going to observe in Professor Woodbury's video. So this is the molecular equation. But we now know that these compounds don't exist in their molecular form. When we dissolve them in water, they exist in ionic form. So this next equation I'm going to write is typically referred to as the total ionic equation. And in the total ionic equation, we write the compounds as they exist as ions in solution. So from before, the barium exists as barium 2 plus, 2 chlorides, 2 sodiums, And we do not write the oxyanion or the ternary anion or the polyatomic anion, however we might want to refer to this, we do not write it as something like this, right? That would be absolutely incorrect, or any form that up. The SO4, the sulfate, stays together. Okay, so I have identified, not quite. So that I have identified what it starts off at, and it forms, let me do the easy part. We know that sodium chloride is soluble, but we also know that barium sulfate is insoluble. It is the solid compound that we saw. So we cannot write it as ions because that is not the way it exists. There is barium sulfate. Now, there are a couple of different ways you can identify this as a solid. The first is to put parenthetically for S in there for solid. I am in the habit of underlining it as a habit that is about 40 years old, and I'm not going to break it now. Either way is acceptable. The book uses this way to do that. So this now is the total ionic equation. Well, you can see that if we treated this as an algebraic equality, I've got everything here on the left, I've got everything here on the right, and I see sodium here and here, chloride there and there on the same or on opposite sides. And so if I simply subtract them from both sides, as it were, or cancel like terms if you prefer that expression, then I get this expression, which of course we call a chemical equation. This is the net ionic equation. Because it has eliminated these ions that are on both sides. Now, I'm going to provide some more vocabulary for these, because these are the ones that have been canceled, and we call them spectator ions. And the word comes from the idea that they are just watching, kind of like spectators at a sporting event. They are not participating. They are simply there kind of watching everything. They are there at the beginning, they are there at the end, and they have not changed. So there, that is the chemical reaction for barium chloride. Okay. So what I have here are some pictures of barium X-rays or barium enema X-rays or barium test X-rays. They go by a number of different names, but the idea is all the same. And while I discuss these in a moment, first let me point out that barium chloride, the first material we looked at, is really quite toxic. It is toxic largely because the barium ion is toxic to the body. Frankly, I don't recall what. You could look up perhaps the LD50 for barium chloride to get an idea of its toxicity. Nonetheless, barium chloride really is quite toxic. However, barium sulfate, the precipitate that we saw, is quite non-toxic. And it is non-toxic because it exists in molecular form. It does not dissociate to any discernible extent to create the barium ion. As a result, people are often, if they have a problem with their gastrointestinal tract or GI tract, perhaps a piercing in the bowel or a piercing in the stomach or an ulcer or any one of a number of problems that might occur with the GI system, they are often asked to either swallow or get a barium enema, where the barium sulfate solution, that white opaque solution that you saw, is taken into the body. And then at a reasonable time thereafter, an X-ray is taken. And so you can see this particular X-ray. I think this is the small intestine, or maybe it's the large intestine. Pardon me, my physiology is not that great. And there's a large contrast. You can see where the barium has filled that part of the GI system. If there is a hole, perforation in any of it, then the technician or the doctor would be able to see literally where it's leaking out. So, the idea of the importance of this really does show through. Okay, so I'm going to, again, pause, be back in a moment. Okay, I'm back again. I've got a few things here. You can, let me get that real close. There you go. You can see that that is a fairly large chunk of iron 3 chloride. And you can see it's yellowish orangish, which is the indicative color for the presence of the iron 3 ion. You have certainly seen, well, I hope you have, in your life sometime, rust. Rust is just iron oxide, a complex form of it. And that rust color is, again, the result of the presence of the iron 3 ion. So any compound that contains the iron 3 ion is going to have that color. So let me write on here. It's always good to have a listing of what's in there. Okay, so this is my iron 3 chloride, and I'm going to set that right this side here and let it dissolve a little bit. And then this next one is sodium hydroxide. And this one behaves very much like, well, it is an ionic compound. It behaves very much like a compound of a metal and a non-metal. The hydroxide ion by itself, again, behaves, again, very much like a metal and non-metal. Gotta take the top off this. So perhaps you can see down there in the bottom, let me get a couple little white pellets, very representative nature for sodium hydroxide. So I'm going to put some water in there. Go. Now I come back to this one, and let me swirl it just a little bit, maybe stir it up a tiny bit. So you can see the solution has become or is beginning to turn slightly orange, which again tells me that the iron is dissolving because now it's in solution. Now, the sodium hydroxide, it's hard to tell that it's dissolving. It doesn't show real well in this, but I can see some density currents in there. But this should give me a good idea. No, not much has dissolved yet. There we go. The light bulb is on, so that solution is certainly becoming not saturated in, but it's certainly dissolving the sodium hydroxide. So I'm going to stir that around a little bit more. And just for good measure, right, light bulb there, definitely on. Okay. Set those right there and share screens for a moment. So in a moment, I am going to demonstrate the reaction of iron chloride and sodium hydroxide. Now, We'll see some solubility rules later that help us predict these things. But this reaction will either be a double displacement reaction, or there will be no reaction at all, right? So in this case, the cations will swap and the anions will swap, or there will be no reaction at all. It is the case oops, shame on me. I, of course, had that wrong because the 3 goes on the outside so that there's 3 of them and sodium chloride. And now I'm going to come back and demonstrate this one. So let me get that in an appropriate location. Side. There we go. So on 3, 1, 2, 3. Right. And you can see the solid formation in there. It doesn't show quite as good as I'd like. Let me hold it up real close to the camera. And I think you can see, let me see if I can get some light in here that might help a little bit. But you can see there, it's beginning to settle out already, right? The solid is getting there, and I'm going to hold that there for a moment. Actually, maybe I'll come back to it. So I'm just going to let that sit there for a while. So we observed a chemical reaction, right? We did an experiment, we added 2 things, we made an observation, and the observation is that a solid formed. So if our observation is a solid formed, then we conclude properly that there was a reaction that occurred. And this is the only potential double displacement reaction. Now, we know again from previous and from other experience that sodium chloride is soluble, so that the only insoluble compound can be the iron 3 hydroxide. Let's balance this equation. We have the proper products, can't balance it until we have the proper products. Again, this one balances pretty trivially. I see I have 3 hydroxides here. I'm going to go over here and write 3. Now I have 3 sodiums here. I'm going to come over here and write 3 chlorines. I come over there, 3 chlorines, 1 iron, 1 iron. Voila, it's balanced. This is the molecular equation. So what's the total ionic equation? And later on, you may see me abbreviate this TIE for total ionic equation. Well, the iron is soluble and it is ionic. So it exists thus. The 3 commutes through. Excuse me. So that's everything on the left. On the right, the iron hydroxide is a solid. The sodium chloride remains as ions. So that's the total ionic equation right there. And the net ionic equation is simply this. And it suggests that anytime that iron 3 cations are in the presence of hydroxide ions, then they will react to form iron 3 hydroxide as a solid. And again, the sodium and the chloride are spectator ions. So there's my reaction right there. So again, I bring this back. You can see it's beginning to settle out a little bit. Now, if I were to leave this sit out for a day or two, it would all very much settle onto the very bottom of the beaker, but unfortunately, we don't have that much time. So now what I would like to demonstrate is, oops, where did I put my small beaker? There it is. Now what I would like to demonstrate is the conductivity of a molecular compound. Now, we have already done this. We did the conductivity of water, but this next one, just for a little bit of variety, is methanol. Now, methanol is similar to the chemical ethanol. It is an organic compound. The formula is CH3OH for methanol. And from your perspective right there, you see a clear colorless compound. And of course, you're going to have to simply take my word for it that it is in fact methanol. But at least in appearances, it's no different than water. Now I put it into the container or onto the conductivity apparatus, and there is absolutely no conductivity at all. So methanol is a molecular compound. That is to say, it does not exist in ions at all. Moment, I'm going to do another compound that you're familiar with. And the other compound that you're familiar with, let's see if I can show that there, distilled vinegar. Now we use, in the laboratory, we call it acetic acid. When you buy it on the shelf at the grocery store, it's vinegar. And again, I'll put the formula up in a moment. But everybody, I'm sure at some point or another in their life has consumed vinegar. It is an exceptionally common ingredient in many, many different types of recipes. So again, I put that in there, got my vinegar in there. Back to my conductivity apparatus. And there we go, just barely, right? The light bulb certainly is not bright, but it is glowing a little bit, suggesting that there is some ions in solution. Okay, so let me set that aside and let's look at what these compounds are. So the first was methanol. It is this formula. Now, we will get into Lewis structures and molecular formulas later in more detail. For right now, it is not critical that you understand this, but these bonds that I'm showing, these lines, represent covalent bonds, right? We've talked about ionic bonds. These lines represent covalent bonds where the electrons are shared. Now, I'm sure that, and certainly hopeful that everybody understands that in basic terms. So each one of these bonds here are covalent bonds, and covalent bonds, with the rare exception, don't dissociate to any significant extent. So the methanol exists in this molecular form, and so therefore doesn't create any ions in solution. So when we have, the message here is, when you are writing the total or net ionic equation for a molecular compound, it must be written as in its molecular form. Do not show it as ions. To write this as CH3 plus OH minus, distinctly wrong. To try to write it at CH3O minus plus H plus for right now is also distinctly wrong. It exists as a molecular compound only. Okay, what was the next one? The next one was acetic acid. And I'm going to write the full line formula for acetic acid. And you can see, again, I have this CH3 piece of the molecule. When you study organic chemistry, you're going to see that this is called a methyl group. And in almost all cases, certainly the ones we're going to deal with, stays by itself. Carbon, double bond to an oxygen, bond, oxygen, bond, hydrogen. It has the formula C2H4O2, but we see how when we write it this way, it doesn't give us an indication of the actual structure of the molecule. It might also be written CH3 COOH to give us a better indication of the actual structure. And again, when you get into organic chemistry, you're going to see and recognize this as a carboxylic acid functionality. Run out of room there. There we go. Carboxylic acid. The total of all this is acetic acid. Now, because this bond right there is a little bit weak, it's not a particularly strong bond, because of that, this molecule will dissociate slightly, giving this piece plus this. And right, this is perhaps, very much dependent on concentration. Perhaps 1% of the molecule will dissociate like that. But that 1% that does dissociate gives ions, which gave rise to the light bulb coming on, at least to a small extent. Okay. So moving on, yes, one last thing. You're going to simply have to get used to me writing this molecule as H to represent this hydrogen right here, and the rest of it as AC. Pardon me, I didn't write it on here. Since the whole thing is acetic acid, this hydrogen is the acid, right? We're very accustomed to recognizing hydrogen as the acid, and what's left is the acetate. So this is how I write acetic acid, and when it dissociates, I write it as H plus AC minus. Okay. So that was acetic acid, that was methanol, and I want to contrast this with one last one. And let me stop the sharing for a moment. Okay, so what I'm holding up here, let's see if you can read the label. There we go, sulfuric acid solution, and can you see there, it's coming into focus, 6 molar. Now, we haven't talked about concentrations yet, but again, I'm sure that most of you recognize the concentration units of molarity or molar. 6 molar in most contexts would be called reasonably concentrated, but that reasonably concentrated, very concentrated, those are not highly defined terms. Nonetheless, 6 molar sulfuric acid is reasonably concentrated. And I want to talk a little bit about the hazards associated with sulfuric acid for a moment. Because there is this belief somehow that all acids are just going to dissolve whatever they come in contact and are tremendously hazardous. And that is absolutely true for some. Concentrated sulfuric acid, the most concentrated that you would typically be able to buy, is 18 molar. It is exceptionally hazardous material, and I would not be working with it in this context if that's what I had. It causes immediate burns to skin. I think we've talked about it a little bit. The sulfuric acid I have is 6 molar. Because there has been quite a bit of water added to it, it is notably less hazardous. Not non-hazardous, just notably less hazardous. So I need to pause for, oh, pardon me, pause for a moment, in a moment. Sulfuric acid is a strong acid, whereas acetic acid was a weak acid. So when I say something is a strong acid, I mean that it dissociates 100%. All right, and so now let me demonstrate the sulfuric acid. Oops. I realized that I may not have been sharing a moment ago. Rats. So let me again just put this up here to show if I was not sharing, pardon me, right there's the information on acetic acid that I was discussing. Let me get it up there. I'll like take a look at that. And of course, what I was discussing on or with respect to the sulfuric acid. Okay, so now I have this here. And I'm going to pour some of the sulfuric acid in here, again, 6 molar. Actually going to dilute this a tiny bit. Now, because of the nature of the monitors, you might not be able to tell just how bright that bulb was because the camera on the computer doesn't really capture it. It was intensely bright, in part because it is concentrated, right? The more ions, the more conductivity. It gives 2 ions per, it dissociates at 100%. Back. And I now want to fill in these ideas of strong and weak acids a little bit more than I already have. So again, in the context of writing chemical equations and specifically total and net ionic equations, acids are either strong, and that means they dissociate, or weak, which means they dissociate only weakly. So a strong acid dissociates 100%. And again, the word dissociate, disassociate. Strong acids. There is a method of determining this. For right now, I am simply going to list the things which are strong acids. It is not a complete list, but it is a good list. Those 3, these are the binary acids: hydrochloric, hydrobromic, and hydroiodic. Now, as we've discussed before, typically you should write AQ. And for now I'm going to, but again, just recall that, you know, I started off discussing these as acids, and so the context in which I'm discussing them made it clear that they were dissolved in solution. We then have HClO4 perchloric acid, HClO3 chloric acid, H2SO4 HNO3, nitric acid. So when you see one of these in a equation where you're trying to do or determine the reaction, and trying to determine the total and net ionic equation, excuse me. All of these get written as ions in solution. If it is not one of these, then it is not written as ions in solution. So while there are exceptions to what I'm telling you, you're not likely to run across them until Chem 1B, and so we're simply not going to worry about them at this point. Weak acids. Weak acids don't dissociate 100%. Typically, they dissociate less than 1%, sometimes 1/100%, sometimes a 10,000th of a percent. That would be a very weak acid. This includes acids such as HNO2, nitrous acid. It includes this acid, H2CO3. Oops, this is nitrous acid. It includes carbonic, it's not E, that's a C, carbonic acid, something that dissolves, something that deserves a little bit more discussion in a bit. Let me scroll. We have already seen HAC, and again, I'm going to write this with the understanding that you know that the molecular formula is a bit different. Let's see, what else are we likely to run across? That one is sulfurous acid. Now, whereas the list that I gave you for the strong acids is as complete as we need it to be, what you need to know is if it's not one of the strong acids, then it is a weak acid. I can't list all the weak acids because there are literally thousands, if not tens of thousands of weak acids. So something is a weak acid if it's not listed amongst those very few strong acids, and they dissociate much less than 1%. I want to take particular note of that particular acid, because you're going to see what I'm going to show you in Professor Woodbury's demonstration, and you're going to need to get the reactions right associated with that. So carbonic acid is the acid that is present in any carbonated beverage, right? Whether that's soda, champagne, beer, any carbonated beverage has that carbonation as a result of the presence of carbonic acid. Now, I haven't done this, I don't think, thus far, nor will I be doing it too much in this class, but I'm writing now a double-headed arrow to indicate that the reaction really goes in both directions relatively equally. And it can dissociate to carbon dioxide and water. So while the solution contains carbonic acid, when you pull the lid or pop the top or whatever it sees, and then you see the bubbles, those bubbles are carbon dioxide that are being given off because the reaction is moving in that direction. So as long as the lid is off of the container, the reaction continues moving to the right, generating the CO2 gas. And of course, whatever that beverage is, champagne, beer, soda, if you leave it out long enough, all of the carbon dioxide gas evaporates, all the carbonic acid is gone, and we say that the beverage has gone flat, that is to say, in the absence of CO2. So we need to recognize that anytime we write carbonic acid, it's really water and carbon dioxide, or vice versa. Now, this is important, for example, when you see reactions such as this. Sorry, I don't have these materials. I couldn't demonstrate them to you. You're just going to have to believe me on this one. There is sodium carbonate. Oh, let's add HCl to that. And I will go ahead and write this one as aqueous. And of course, I'm not going to write it again. It just added it. just means too much writing to potentially confuse other issues. The sodium carbonate is also aqueous. So it reacts to form, in this case, it's a double displacement reaction or nothing. The carbonate is -2, the hydrogen is +1. So jumping right to the completely balanced chemical equation for that one. Sodium carbonate plus 2 hydrochloric acids react to give carbonic acid plus sodium chloride. Well, that's all well and good, and that is correct. However, when you combine these two materials, the observation will be that bubbles form. This is not a gas. This is not a gas. So where do the bubbles come from? The bubbles come from the subsequent reaction, right? So this reaction forms, or this material forms immediately, and then this reaction right here forms immediately after that. So your observation of bubbles is the formation of carbon dioxide, which was in turn formed from the carbonic acid that reacts here. So here is the molecular equation here. The total ionic equation would start off something like this. And there's a couple of different ways, both of which I find acceptable to write this. There's everything on the left. Carbonic acid is a weak acid. It does not exist as ions because it does not dissociate. So we write it in its molecular form. So this is the total ionic equation. And since I don't want to rewrite everything, the net ionic equation is what remains. So this is certainly one acceptable way of writing that equation. Another acceptable way, at least to me, is to write it this way. Pardon me, I'm gonna erase that, come back to it. Let me do it this way. Start with the molecular equation. And in this one, the difference here is I have written the carbonic acid directly as H2O plus CO2. And so now the net ionic equation, pardon me, I'll do the total ionic equation. Starts off very much the same way. Sodium carbonate, ionic compound, soluble, written as ions. HCl, strong acid, written as ions. H2O, molecular compound. We know it's a molecular compound because it's formed from two nonmetals. We know it's a molecular compound because the conductivity, because it didn't have any conductivity. Carbon dioxide formed between two nonmetals. It doesn't contain any ions. So again, we write it in its molecular form. And 2Na plus 2Cl minus. Now, the way I have just done it really is the more correct way. I'm just simply telling you the other one is understandable and at least for this point acceptable. So this is the total ionic equation as you see it here. But as before, if I cross off these, then I get what is left, or the net ionic equation, and that is that two H pluses plus carbonate combines to form H2O and carbon dioxide gas. And thus ends our discussion. Thank you very much. We'll see you in class.